Welcome to the lecture video for 3.2. Section 3.2 in the textbook covers sequences. And we've actually already started this topic a little bit in our discussion of Taylor polynomials and how to recognize the pattern in their coefficients. This will be our main motivation for learning more about sequences, but keep in mind that they're an interesting topic in math in their own right. So the main goals in this lecture, and this will be on the shorter end with only a few examples, will be to practice with the notation to describe the terms of an infinite sequence. We won't talk about finite sequences, but they're also a thing you can study using notation. And finally, the main topic will be to calculate the limit of an infinite sequence, given any of the notations we learn in part one. Let's get started right away with the definition of a sequence. What is a sequence in math? We'll have three different ways of thinking, or three different notations for thinking about them, but don't be confused by these three different ways. The simplest way to understand what a sequence is just to think of it as a list of numbers. So the technical mathematical definition is a sequence is an ordered set of numbers. All this means is that it's a list of numbers and it matters what order the numbers show up in. We can have a finite or an infinite list of numbers. If the sequence is finite, we'll call it a finite sequence, but in general, we won't be interested in these as they're sort of boring in some sense. If there are only finitely many numbers on the list, they can only be used for certain types of situations. However, with an infinite sequence, if the sequence has a formula for its nth term given by some actual formula, some function of the index n, then they become extremely powerful for describing things like, we've already seen them for Taylor polynomials, but even for the technical definition of a Riemann summation, any of our different rectangular trapezoidal rules have sequences for their coefficients. So there are three different notations, and there are actually some variants on these notations you'll see as well. But the three different notations for a sequence are, first of all, a list of the numbers in the sequence. The far left one here at the bottom, the numbers in the sequence are 1/2, 2/3, 3/4, 4/5, etc. And you'll see them either show up in curly brackets like this with a ... at the end to indicate this pattern continues, or sometimes it'll be written with a round parentheses. You'll see those interchangeably, but the idea here is this is a list, and the sequence is the entire object, the entire symbol you see. Everything inside of the parentheses belongs together. They're sort of falling into some pattern. If we can recognize that pattern, we can also write the sequence as a single curly bracket or parentheses, sometimes even without these indices from 1 to infinity on the outside, but we'll leave them here for now, of just the formula for the nth term in the sequence. So the sequence here starts at n equals 1. We'll typically take things starting at n equals 0 or 1, but there's no reason you have to do it that way. And if you plug in the number 1 and then the number 2 and then the number 3, and you keep going for any positive integer you want to plug in, it will tell you that number in the sequence in that order too. It'll tell you the position, n equals 1, 2, 3, and so on. And the output of plugging things into the function tells you what the number is in the lineup. Finally, we'll also write things directly as a function of n. Now, we're used to thinking of functions as f of x. Here we'll use the subscript notation, a sub n, to denote a sequence, to distinguish it from functions. But you should think of this as a rule for plugging in different values of n, and each one gives a new term in the sequence. As we increase n, we fill out the whole sequence. So those are the three notations. We use all of these interchangeably. The main importance of a sequence is not just writing down a formula for its pattern, but deciding if the sequence converges or diverges. This is the main power of using sequences in calc class. So just like with functions and limits, the notion of the limit of a sequence is abstractly, if we can make things close to some target, we'll call that the limit. So that's sort of not a rigorous definition in math class. And in your Calc 1 class, you may have learned something about an epsilon delta definition of a function limit. There's something similar for limits. You won't be strictly required to learn it for this class, but I'll talk about that later in the video a little bit. Actually, I'll talk about it in a couple slides and then not talk about it so much later. And also in class, in the classwork activity, you'll see a formal definition of this given. So the definition that we'll use, and you will have to know for this class, is that a sequence an, so thinking of that an as telling you the terms of the sequence, has a limit L which is a number, if we can make the terms of the sequence as close to that L value we want by choosing terms further down the sequence. And the more precise way to say this is for any target threshold we pick, so pick some number of decimals of accuracy to get within that threshold of the target L. All of the terms of the sequence past some cutoff have to be within that threshold or within that accuracy of L. We will do one example of this in a moment to practice with this definition if this is the first time you're seeing it. But again, it's essentially identical to the definition for functions of x, except here we don't have to plug in all x on the real number line past a certain point. As x goes to infinity, here we only have a discrete set, all of the numbers from 1 to infinity, just the integers. If a limit exists, just like with functions, we'll say the sequence converges. If the limit does not exist, we'll say it diverges. Again, similar to with limits of real valued functions. So here are a couple comments that I want to make before we get started with an example. And the first one, which sometimes is a little misleading, this doesn't happen so much with functions. We don't get confused by this as much. But with sequences, there are infinitely many terms in an infinite sequence, but the first finitely many, and it doesn't matter how many you choose, but only finitely many terms do not determine the limit. So theoretically, it could be possible that the first 10 million terms of the sequence don't have any discernible pattern, but starting with the 10 million and first term, there becomes a pattern that eventually gets close to some target, and then that target is L. So in practice, this is rare, but you just should be aware that the first few terms of a sequence don't determine its end behavior or its limiting behavior. It only matters what happens after a certain cutoff and then off to infinity. As long as that continues, that's the limit. To make the definition a little more precise, and we'll do this with the next example, to say arbitrarily close, again, means that if we pick a target threshold or an accuracy threshold, let's say within 1/100th or 1/1000, or in this case, 1/millionth was the, I think I didn't put commas in, but the last fraction there is a millionth, then we can choose a cutoff, and past that cutoff in the sequence, every term is within that threshold of accuracy of the true limit. You'll see on these slides there are a couple static visuals like this, which if you go click on the interactive version of the slides on Canvas, you can actually play around with these slider bars. What you should think of here, and the way that I like to remind myself of what's happening with limits, is we're really playing target practice. So let's suppose that the math gods hand you down an accuracy, and they say, on this problem, you need to get within some number of decimal places. You can think of that constraint as putting a band around our potential limit, which is this blue line. Here, the L equals 3 is the potential target of the sequence. And we can put a golden band around that target that the math gods tell you the width of. And your job then, to prove that the sequence converges to 3, is to show that if we move far enough to the right in our sequence, every value stays within this golden band. Now, it's not enough to do that for a single, we call these epsilons, the width of these bands. It's not enough to do that for a single width or a single distance away from the target. You have to be able to do that for any positive distance or any width of the golden band. So it's target practice, and you're told the target, and you have to figure out how far along to shoot in the sequence to guarantee you always land within the target range. Let's compute the next, this first limit together. This was actually the sequence that we showed with 3 notations on one of the first few slides. And before I switch over to my tablet and write some things about the sequence, I want you to stare at the terms in the curly brackets, or stare at the formula, or both, and come up with a guess. So pause the video if I keep talking when I switch over if you haven't made a guess yet, but I want everyone to have a guess in mind, and then we will show how to demonstrate that the guess is correct. Okay, have you picked a guess yet? Just looking at these fractions, 1/2, 2/3, 3/4, 4/5, I noticed 2 things. First of all, they're increasing. These fractions keep getting larger than, and if I write them as decimals, it becomes more clear. We start at 50% or 0.5, and then by the time we get to 4/5, we're up to 80% or 0.8. The other thing I notice is because the denominator is larger than the numerator, I'm never going to get larger than 1 every term in the sequence it fits the pattern n over n plus 1. So if I'm increasing and I can't escape the bound 1, it seems reasonable to guess that the limit here is L equals 1. So let's take that as our guess, and it's okay if it's wrong, but if it's right, then we should be able to demonstrate it. So the idea here, this is the mathematical way of writing the golden band and trying to pick a cutoff past which we're always within that target region, is to look at the difference between the terms of the sequence and the true target that we're guessing. So in this case, we're going to look at the difference between the values of the terms of the sequence and the number 1. And let's get a common denominator to make this a single fraction and study it better. So this will be n plus 1 over n plus 1. This is how far we are away from the blue line or the target in the picture. We want to somehow constrain those distances. So the numerator is n minus n plus 1. That'll give me a minus 1. I'm just going to apply the absolute values right away and get a positive 1. And then the denominator is that common denominator of n plus 1. You can think of this as an error bound in some sense, just like we've done in a couple previous techniques. And as we increase n, the error goes to 0. So this is actually already a proof, although we haven't written out all the details, that the error goes to 0 as n increases, meaning the terms of the sequence get arbitrarily close to 1. To make this a little more rigorous, if we pick an accuracy, or like I said before, the math gods hand us down some accuracy threshold, you must be within, let's say, 6 decimal places of our target value of L, which we're pretty certain now is the limit. Then this scratch work above, where we looked at the differences between sequence terms and target, actually give us a recipe for producing a cutoff. So if we have to be within 6 decimal places, that's going to be 1/1,000,000th of the true answer. Then notice I can turn this whole inequality, the left side we already computed, a little easier, as 1 over n plus 1 over is less than 1/1,000,000th. And if I solve this inequality for n, I'm actually going to get, I'm not going to fully solve it. I'll get n plus 1 is greater than 1,000,000. That just means that I have to choose n at least that, n at large enough so that n plus 1 is at least as large as 1,000,000. For example, I could choose n to be anything, 2,000,000. I could be really inefficient and choose some large n. The point is, eventually we are within the target threshold. These differences are smaller than the required accuracy, so our sequence converges to L equals 1. If you take analysis class later in your math career, or you take some other calculus class where limits are more seriously involved, you will do a lot more practice using this version of verification for a limit. What we're going to do shortly, and this will be the next topic we talk about, is use our knowledge of function limits instead to evaluate sequence limits faster. So this will be the last time that we have to officially prove a limit, even though we didn't even write all the steps together. By the way, here's a graphical depiction of the example that we just solved. The target threshold, the target value here, the blue line, is L equals 1. And no matter how small we draw the golden band, you'll be able to play with the slider bars here to make it smaller. There are always infinitely many terms to the right of some cutoff. For in this current picture, it looks like past n equals 3, the third term in the sequence and beyond, that all of the values of the sequence stay within that distance of the target L equals 1. So the main theorem that we'll be using to evaluate limits is as follows. Suppose that we have a sequence an that we're studying, and we can separately find some function f of x, a real valued function, so that when we plug in integers n into that function, they recover the values of the sequence. You can think of this as you have some formula with n giving the terms of the sequence, and if you put an x instead of an n, then you actually have a real valued function. Or at least if you plug in large enough n values, they all fit this pattern. So the theorem then says that the power of this theorem says that if the limit as x approaches infinity of f of x is L, or in other words, if f has a horizontal asymptote at positive infinity of L, then we can conclude that the limit of the sequence an is L as well. Another way to say this is that if you have a real valued function whose integer points are the sequence you're interested in, then the asymptote of the function is the limit of the sequence. Here are 5 practice examples, and we're going to do all of these together, but this is a good opportunity to test your skills with asymptotes of real valued functions. You can use the theorem that I just showed you to solve all of these problems. And I want you to think about, if you plugged in x instead of n, how you would solve that limit. And I'm going to switch over and we'll do them together, but I encourage you to pause and at least think through, if not write out some details of each of these as a function of x. While you're doing that, if you're still listening, thinking about any of these, I'm going to take a drink of water. Okay, so I'm actually not going to convert any of these back to x notation. I'm just going to use the principles that we know from function limits, from limits at infinity of real value functions to solve these problems. For example, here, if I had 2x over x plus 3, that's a rational function, and the degree of x is the same in the top and bottom. The way to solve this in general would be to divide both numerator and denominator by the highest power of x. So I'm just going to take the same approach and use the highest power of n, which is n to the 1 in both cases. Notice that I'm going to keep my limit simple in every step until I'm able to evaluate it. In the top, we'll get 2n over n is just 2. In the bottom, n over n is 1, and 3 over n is, well, that's 3 over n. And here we see we're able to evaluate everything here. 3 over n goes to 0 as n gets large. This is the principle that, or you can, the graph of 3 over x has an asymptote of y equals 0, or the principle that the denominator gets heavier than the numerator, and therefore we have a limit of 0. That means the entire expression goes to 2 over 1 or 2. So this limit, this sequence 2n over n plus 3 converges to the value 2. A similar proof, by the way, will confirm our guess of L equals 1 in the previous example, even though we did some more work to already show that for ourselves. We can prove it using this theorem. What happens with part B, the limit as n goes to infinity of 1 over n cubed? Well, these are fractions whose denominators are just getting heavier directly in the example. If this were the function 1 over x cubed, we know that that function, by graphing it or by using limit techniques from Calc 1, has a horizontal asymptote of y equals 0. So by the theorem we just learned, this sequence has a limit of 0 as well. It converges to 0. How about part C? E to the negative n as n goes to infinity. Well, this is a good example where we should graph the function e to the x as x goes infinity is a different function. We really want to graph e to the negative x, which is going to look like just a mirror image reflected over the y-axis of e to the x. And you can see this function has an asymptote, has a horizontal asymptote at y equals 0. Or you could also think of this as the fraction 1 over e to the n, and then the denominator is getting heavier again. We're not going to be super precise in this class, but you should be able to justify these things if asked about them. Why is this 0? Well, there's a couple reasons. Graphically, you can think of we're plugging in just these integer points on the graph, or algebraically, the fraction idea. Okay, part D looks a little more complicated. We have 2 types of functions. There's an algebraic one in the top, n squared, and then an exponential on the bottom. And you may recall from Calc 1 that exponentials usually win the race. We'll talk about this in the context of sequences in a moment. But if this were the function, and I'm actually going to replace this and do this a little more precisely with a function of x, so we can use some more techniques from Calc 1 and function limits. In this case, I see that the top and the bottom are both going to infinity. So I can use L'Hopital's rule, I'll abbreviate it L apostrophe H, to reduce the complexity of the numerator and denominator of the function. L'Hopital's rule says that if I have the form infinity over infinity, that's an indeterminate form, I can take the derivative of the numerator and denominator. And after one step of L'Hopital, I still have 2x going to infinity over e to the x going to infinity. So I'll do one more step of L'Hopital. You can think of this like a hammer, and we only hit the nail down halfway. Let's hit it again until it's gone. So we're left with 2, the derivative in the top, and e to the x. And similar to the previous problem, as x goes to infinity, this is 2 e to the minus x. Written another way, this converges to 0. So far we had 4 different sequences, all of whom we could interpret using real valued functions of x, and they all converge to something. 3 of them converge to 0, interestingly enough. One of them converged to 2. In part E, things are a little different. So I don't actually know a good function. I don't know how to raise -1 to different real numbers other than integers. So I can't actually replace this with something like -1 to the x. And that even already becomes an issue if we raised a fractional, if x is a fraction, not even anything like pi. For real numbers x, how do you take the square root of -1? Well, there's no real number that does that for us. That's in the realm of complex numbers. But in this case, let's just use our intuition about how to get the limit value of a sequence. And I'm going to actually graph this to study it a little bit closer. So let's graph the terms of the sequence. I'll do it in purple. For n equals 1, we'll have -1. For n equals 2, we'll have +1. N equals 3, -1, 4, +1. And there's 2, and they keep going on like this forever. So the terms of the sequence are all either positive or -1, just plugging in those n values to check. And you can see it visually. We're never going to get within a certain target range of any value. Let's say our guess was, the average of these values is 0. Maybe let's just pick the midpoint. Well, as soon as I draw a golden band around that, that's within distance 1 of that target of L equals 0, all of the values will stay outside of the band. So we're kind of in trouble there. If I say, let's just pick half the values or L equals +1, if you draw a band around those values, then the -1 values are too far away. So you're kind of always out of luck. And in this case, we'll say the sequence diverges. And just to write a couple words, the values -1 to the n never get arbitrarily close to any real number L. Doesn't matter what L you pick for a target. They all of the terms of the sequence are unit 1 away from, or sorry, actually unit 2 away from some infinitely many other terms of the sequence. They alternate and stay pretty far from each other. So there we go. That's a few limit techniques, most of them using functions. But if you can't use a function, sometimes it helps just to think about what's actually going on in the sequence. There are a lot of properties, and I'll list more of these on the classwork for you. There are a lot of properties from function limits that carry over directly to sequences because of the previous theorem. For example, if I have 2 sequences, an and bn, and they both converge to some numbers L and m, then the sum of those sequences, we'll call it Cn here to be concise, but the sum an plus bn also converges to the sum of their limits L plus m. Written out as a theorem, it seems more complicated than needed because in practice we split up limits of expressions along the plus and minus signs, and we can do other things like multiplication and, in certain circumstances, division. One last comment. This will be the last thing that we do together in this video, at least, is to talk about how to decide when we have different functions in our limit to compare, which ones win the race, so to speak. So the official term in math is if a function dominates another function. And the definition is that f dominates g if when we take the limit as x goes to infinity, and these are now real valued functions, of the ratio f over g, then we get either plus or minus infinity, or this diverges. The notation for this is actually instructive. F is greater than g. We'll read this as f dominates g. This means that f grows faster than g. As we plug in larger and larger values of x, the output values of f tend to crowd out the values of g, or tend to overshadow them. If you make a comparison between different types of functions, kind of like in our ILATE acronym, I'll just focus on exponentials and then 2 different types of algebraic functions. We can make the following comparisons, and you'll see that exponentials always dominate all polynomials, no matter how large the degree. And polynomials always dominate all root expressions, meaning square roots, cubic roots, fourth roots, so on and so forth. You can make even finer distinctions between each or within each of these types. For example, with exponentials, we could have a base of e or a base of 10. 10 is larger than e, and larger bases will dominate smaller base exponentials. Likewise, larger degree polynomials dominate smaller degree polynomials. And with roots, smaller power roots dominate larger power roots. And this is an interesting one. You should think about why that's true. We can talk about it later together. This helps us with sequences because if we have a sequence that's interpolated or is the integer values of some real valued function, then as n goes to infinity, the dominating functions will dominate the other real valued functions, and the corresponding sequences will dominate each other in the same fashion. So for let me just go back a second. Sequences with exponentials dominate sequences that are polynomials. And for example, part C, I think it was in our previous example, had this phenomenon. We were able to evaluate it using L'Hopital's rule, but in the future, you can just say that one of these dominates the other. Another one that we need to know, and we see this in the coefficients for Taylor polynomials, is the factorial sequence, n factorial. The sequence goes 1 for, let's start at n equals 0, like we do with polynomials. 1, 1, 2, 6, and then from there they get larger, 24, 120, and they get kind of out of control after that. Because these terms get so large, n factorial dominates everything else on our list so far. So it dominates even exponential functions, which were so far, pretty like, they were kind of the hot shots of our function domination ordering. And factorial dominates exponentials, and therefore it also dominates everything else further down the list. We didn't have logarithm on the list, by the way, but logarithm is the weakest of all of them. It's dominated even by roots. So here's some summary questions, and then I'll leave you with an exercise or two. First of all, why do we use n instead of x as an index for a sequence? Next, describe 3 different ways of denoting a sequence and talk about how they relate to each other, how to get back and forth between them. Third, when is the limit of a sequence equal to the limit of some function? And finally, if an is obtained from a different sequence bn by adding 1,000 to all of its terms, at least for the first, looks like 2 million n, what does that tell us about the limits of an and bn, if anything? Here's a question from the textbook to think about. So let's consider the sequence an equals n times sine of pi n. Notice that this is not a function of x, it's a sequence. It's an infinite sequence. But if we compare it to the function f of x given by x sine of pi x, and look at the limit as x goes to infinity, asking for a horizontal asymptote, what is the horizontal asymptote of this function, if anything? Does that limit exist? On the other hand, in parts B and C, if you write down a few values and then guess about the limit of the sequence an, what is the limit of the sequence? And finally, if there's a contradiction here, if you get different answers, and from the way the question is worded, it seems like you might, how is this explained, or does it contradict any of our theorems we've talked about so far? Because of this example that I want you to work out on your own, it's important to read theorems, especially their hypotheses and conclusions and which is which, in a careful way. And if you mix them up, you might get something that you don't expect. And this example will illustrate this a little bit for you. By the way, here's another example for you to test out. This will be the end of the video now. The main reason we're talking about sequences at this point in class is to study Taylor polynomials, which give us approximations to real valued functions. However, the sequences are not related to those functions in the way that they have been in this video. They instead are composed of certain derivatives of the function evaluated at certain x values and then divided by n factorial. Those are coefficient sequences in front of all of our powers of x. And those sequences are important for understanding the convergence or divergence of values of these Taylor polynomials. We want to get within certain target ranges of true values of functions, and understanding those coefficient sequences in the long run will be an important tool for us in this class. So this example asks you to work out the Taylor polynomials as a sequence of polynomials for a new function, or rather a function we haven't done this for yet, ln of x. We'll talk about this one on the classwork a little more, but I want you to work out these on your own before coming to class. So thanks for tuning in, and I will see you for the next video.